The oldest light in the universe is still shining quietly, faintly, and all around us. It's not the glow of distant stars or the shimmer of galaxies. No, this light is something far more ancient and mysterious. It's the cosmic microwave background radiation, a ghostly echo of the Big Bang itself, lingering in the fabric of space like a cosmic fingerprint. This faint glow, invisible to our eyes, carries secrets about the universe's earliest moments, secrets that have transformed how we understand everything from the birth of galaxies to the invisible forces shaping our cosmos. What can this ancient light tell us about where we came from? How does it hold clues to the elusive dark matter and dark energy that make up most of the universe? And why is this discovery, made by accident decades ago, still one of the most profound breakthroughs in science? In this video, we're going to dive deep into the story of the cosmic microwave background radiation, the science behind it, the history of its discovery, and the incredible insights it continues to offer. By the end, you'll see why this faint whisper from the dawn of time is so much more than just a relic of the past. It's a window into the very origins of existence. Let's begin. Picture this, an unimaginably small point packed with all the energy and matter that would one day become galaxies, stars, and planets. Then, in an instant, it explodes. This is the Big Bang, the moment our universe burst into existence around 13.8 billion years ago. In that first fraction of a second, the cosmos was a seething, chaotic sea of energy and particles, so hot and dense that not even light could escape. But as the universe expanded, it began to cool. Over hundreds of thousands of years, it transformed from a blazing inferno into something more familiar, like a cosmic soup simmering down. Then something extraordinary happened. The universe cooled enough for protons and electrons to combine, forming the first atoms. Suddenly, light, which had been trapped in the chaos, was finally free to travel. This moment, roughly 380,000 years after the Big Bang, is when the cosmic microwave background radiation was born. Think of it as a kind of cosmic afterglow, a faint whisper of light left behind by the universe's fiery birth. This ancient light is like a fingerprint, a unique mark left by the Big Bang itself. It carries with it the imprints of the universe's earliest moments, the ripples and fluctuations that would one day grow into galaxies and clusters of galaxies. And just as a fingerprint holds clues about a person's identity, the CMB holds secrets about the universe's infancy. It's a snapshot frozen in time, a window into a period when the cosmos was still taking its first breaths. But how did this light survive billions of years? Why hasn't it faded away? The answer lies in the vastness of space itself. As the universe expanded, that primordial light stretched, its wavelengths growing longer and longer until it became the faint microwave signal we detect today. It's everywhere, surrounding us like an invisible blanket, a silent witness to the universe's earliest moments. What's truly remarkable is that this light isn't just a relic of the past. It's a treasure trove of information, holding clues about the universe's structure, its composition, and even the mysterious forces that govern it. From the seeds of galaxies to the elusive nature of dark matter and dark energy, the CMB is a cosmic time capsule waiting to be decoded. And as we'll see, the story of how we came to discover this ancient light is just as fascinating as the light itself. Sometimes, the most groundbreaking discoveries in science happen not because we're looking for them, but because we stumble upon them while searching for something else entirely. That's exactly what happened in the mid-1960s when two radio astronomers, Penzias and Robert Wilson, made a discovery that would change our understanding of the universe forever. And it all started with what they thought was a pesky technical glitch. Working at Bell Labs in New Jersey, Penzias and Wilson were using a large radio antenna originally designed for satellite communications. Their goal was to study radio waves from space, but no matter where they pointed their antenna, they kept picking up a strange, persistent noise. It wasn't the kind of noise you'd expect from stars or galaxies. It was a faint, uniform hum that seemed to come from everywhere at once. At first, they thought it might be interference from nearby New York City, or even something as mundane as pigeon droppings inside the antenna. They cleaned the equipment, checked for every possible source of error, but the noise refused to go away. What they didn't realize at the time was that this mysterious signal wasn't a mistake. It was the faint whisper of the universe itself. Unbeknownst to them, another team of scientists, led by Robert Dick at Princeton University, had been actively searching for this very signal. They had theorized that if the Big Bang had indeed happened, there should be a faint afterglow of radiation left over from the universe's fiery birth. When Penzias and Wilson finally connected with Dick's team, the pieces fell into place. That noise wasn't interference, it was the cosmic microwave background radiation, the oldest light in the universe. The significance of this discovery cannot be overstated. For decades, scientists had debated the origins of the universe, with some supporting the Big Bang theory and others favoring a steady-state model. The detection of the CMB was a smoking gun, providing the first direct evidence that the universe had a beginning. It was a moment of profound validation for the Big Bang theory and a turning point in cosmology. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for their accidental discovery, a testament to the power of curiosity and persistence in science. But the story doesn't end there. The discovery of the CMB didn't just confirm the Big Bang, it opened the floodgates for a new era of cosmological research. Suddenly, we had a tool to peer back in time, to study the universe not as it is today, but as it was in its infancy. This faint glow, once mistaken for a nuisance, became a treasure trove of information, revealing the universe's age, its composition, and even the seeds of its large-scale structure. It's a reminder that sometimes the answers to the biggest questions are hiding in the quietest places, if only we know how to listen. So, what exactly is this cosmic microwave background radiation, and why is it such a big deal? Imagine the universe as a newborn just 380,000 years old. At that moment, it was still a baby, a hot, dense soup of particles and energy. But as it expanded and cooled, something remarkable happened. For the first time, light could travel freely through space, no longer trapped in the chaos. This light, now cooled and stretched by billions of years of cosmic expansion, is what we call the CMB. Think of the CMB as a kind of baby picture of the universe, a snapshot frozen in time. It captures the universe at a pivotal moment, just as it was transitioning from a fiery, opaque fog into a clearer, more structured cosmos. But this isn't just any ordinary photograph. The CMB isn't uniform, it's speckled with tiny fluctuations, barely noticeable variations in temperature. These fluctuations might seem insignificant, but they're actually the seeds of everything we see around us today. Picture the CMB as a canvas with brushstrokes of slightly warmer or cooler patches. These patches are like the first ripples in a pond, the subtle beginnings of what would eventually grow into galaxies, clusters of galaxies, and even the vast cosmic web that connects them all. Without these tiny variations, the universe would be a featureless void, a blank expanse without stars, planets, or life. But the CMB isn't just a relic of the past. It's also a map, a cosmic blueprint that reveals the universe's composition and evolution. By studying these temperature fluctuations, scientists can uncover clues about the ingredients that make up the cosmos. For example, the CMB tells us that ordinary matter, the stuff we see in stars and planets, makes up less than 5% of the universe. The rest is a mysterious mix of dark matter and dark energy, two invisible forces that shape the universe on the grandest scales. And here's where it gets even more fascinating. The patterns in the CMB aren't random. They follow precise mathematical rules, like a cosmic fingerprint encoded with information about the universe's birth and growth. By decoding this fingerprint, scientists can reconstruct the universe's history, tracing its expansion, its composition, and even the forces that have driven its evolution over billions of years. In many ways, the CMB is like a time capsule, preserving the universe's earliest moments in a form we can still observe today. It's a reminder that the cosmos isn't static. It's a dynamic, ever-changing entity with a story that began long before our solar system even existed. And as we continue to study this ancient light, we're not just looking back in time. We're uncovering the secrets of how the universe works piece by piece, one microwave at a time. So, the next time you hear about the cosmic microwave background, remember this. It's not just a faint glow from the distant past. It's a window into the universe's infancy, a treasure trove of information that's helping us unravel some of the biggest mysteries in science. And as we'll see, the journey to understand this ancient light is far from over. The cosmic microwave background isn't just a snapshot of the universe's infancy, it's a roadmap to its entire structure. Those tiny temperature fluctuations we've talked about, they're not random. They're the fingerprints of the universe's earliest moments, and they hold the key to understanding how everything we see today came to be. Imagine the CMB as a cosmic blueprint, with every slight variation in temperature marking the seeds of future galaxies, clusters, and even the vast cosmic web that connects them all. These fluctuations are incredibly subtle, often just 1 part in 100,000. But don't let their small size fool you. They're the building blocks of the universe. Regions that were slightly denser in the early universe had a stronger gravitational pull, drawing in more matter over time. These dense patches grew and grew, eventually collapsing under their own gravity to form the first stars, galaxies, and galaxy clusters. Meanwhile, the less dense regions became the vast, empty voids we see between these structures. Scientists have spent decades mapping these patterns, using satellites like the Cosmic Background Explorer, or COBE, and the Wilkinson Microwave Anisotropy Probe, or WMAP, to measure the CMB with incredible precision. What they've discovered is nothing short of astonishing. The CMB's temperature variations act like a kind of cosmic fossil record, preserving the universe's earliest structures in exquisite detail. By studying these patterns, researchers can trace the growth of the universe over billions of years, from its fiery beginnings to the intricate web of galaxies we see today. But the CMB doesn't just tell us about the past, it also gives us clues about the universe's present and future. For example, the way these temperature fluctuations are distributed across the sky reveals how fast the universe has been expanding. This expansion isn't uniform, it's accelerating, driven by a mysterious force known as dark energy. The CMB provides some of the strongest evidence for dark energy's existence, showing how it has shaped the universe's structure over time. And then there's dark matter, the invisible scaffolding that holds galaxies together. The CMB's patterns reveal how dark matter's gravitational pull influenced the early universe, causing matter to clump together in ways that wouldn't have been possible otherwise. Without dark matter, the universe as we know it simply wouldn't exist. What's truly remarkable is how much we've learned from this faint, ancient light. It's not just a relic of the Big Bang. It's a tool, a guide, and a window into the forces that have shaped the cosmos. And as we continue to study the CMB, we're not just uncovering the universe's past, we're decoding the very forces that drive its evolution. This brings us to one of the most intriguing questions of all. What else can the CMB tell us about the invisible forces shaping our universe? From dark energy's relentless push to dark matter's invisible grip, the CMB is more than just a record of where we've been, it's a key to understanding where we're headed. And as we'll see, the story of this ancient light is far from over. The universe is full of mysteries, and one of the most perplexing is dark matter. This invisible substance doesn't emit, absorb, or reflect light, making it completely undetectable by traditional telescopes. Yet we know it's there not because we can see it, but because of the way it shapes the cosmos. Dark matter makes up roughly 27% of the universe, and without it, galaxies wouldn't hold together, and the universe as we know it simply wouldn't exist. But how do we know this? The answer lies in the cosmic microwave background radiation. The CMB isn't just a relic of the Big Bang, it's also a map of dark matter's influence on the early universe. When scientists study the tiny temperature fluctuations in the CMB, they're actually looking at the fingerprints of dark matter's gravitational pull. In the early universe, dark matter acted like an invisible scaffold, guiding the distribution of ordinary matter. Regions with slightly more dark matter had stronger gravitational fields, pulling in gas and dust, while areas with less dark matter remained sparse. Over billions of years, these dense regions grew into the galaxies and galaxy clusters we see today. But how do we measure something we can't see? By studying the CMB's patterns, scientists can estimate the amount and distribution of dark matter in the universe. For example, the way light from the CMB bends around massive objects, a phenomenon known as gravitational lensing, reveals where dark matter is concentrated. This bending of light creates subtle distortions in the CMB's temperature map, allowing researchers to map dark matter's presence across the cosmos. What's truly fascinating is how precise these measurements have become. Satellites like the Planck mission have mapped the CMB with such detail that we can now estimate the amount of dark matter in the universe to within a fraction of a percent. These observations have confirmed that dark matter is not just a theoretical concept, it's a fundamental part of the universe's structure. Yet, dark matter is only half the story. The CMB also holds clues to another cosmic mystery, dark energy. While dark matter pulls the universe together, dark energy is doing the opposite, pushing it apart. And just as the CMB reveals dark matter's gravitational footprint, it also provides evidence for dark energy's role in shaping the cosmos. As we'll see, the story of the CMB isn't just about the universe's past, it's about the forces that will determine its future. If dark matter is the cosmic glue holding galaxies together, then dark energy is the force that's pulling the universe apart. Unlike dark matter, which exerts a gravitational pull, dark energy acts as a kind of cosmic repellent, pushing everything away from everything else. It's the reason the universe isn't just expanding, it's expanding faster and faster over time. But how do we know this mysterious force exists? Once again, the cosmic microwave background radiation holds the key. When scientists first studied the CMB in detail, they noticed something unexpected. The tiny temperature fluctuations we've talked about weren't just random. They were a precise record of the universe's expansion history. By measuring how these fluctuations are distributed across the sky, researchers could calculate how fast the universe has been growing over billions of years. What they discovered was astonishing. The universe isn't just expanding, it's accelerating. And the only explanation for this acceleration is dark energy, a force that makes up an incredible 68% of the universe's total energy. So, how does the CMB reveal dark energy's presence? Imagine stretching a rubber band. As you pull, the material thins out and the tension increases. In a similar way, as the universe expands, the light from the CMB stretches, shifting to longer wavelengths. By measuring this stretching, or redshift, scientists can determine how fast the universe has expanded over time. What they've found is a clear pattern. The expansion rate has been speeding up, driven by this mysterious, invisible force. But dark energy isn't just a curiosity, it's shaping the ultimate fate of the universe. If dark energy continues to dominate, the universe will keep expanding at an ever-increasing rate. Over billions of years, galaxies will drift farther and farther apart until the night sky becomes a vast, empty void. Stars will burn out and the universe will grow cold and darker, a scenario cosmologists call the Big Freeze. This isn't just science fiction, it's a real possibility supported by the data we've gathered from the CMB. And yet, there's still so much we don't know. What is dark energy exactly? Is it a property of space itself or something entirely different? These are questions that keep scientists up at night, and the CMB is one of our best tools for finding answers. To study the CMB in such detail, we've developed some of the most advanced instruments ever built. Satellites like COBE, WMAP, and the Planck mission have mapped the CMB with unprecedented precision, revealing its subtle patterns and temperature variations. These missions have given us a clearer picture of the universe's history, composition, and future than ever before. But they're just the beginning. New technologies like next-generation telescopes and space probes promise to take our understanding of the CMB and the universe to even greater heights. The story of the CMB isn't just about the past, it's about the forces that will shape the universe's future. From dark energy's relentless push to the mysteries of dark matter, this ancient light is more than a relic of the Big Bang, it's a guide to the cosmos itself. And as we continue to study it, we're not just uncovering the universe's secrets, we're charting the course of its destiny. Mapping the faint whispers of the cosmic microwave background requires tools far beyond what Earth-based observatories can provide. Enter space-based satellites like COBE, WMAP, and Planck, three groundbreaking missions that have revolutionized our understanding of the universe's oldest light. These orbiting observatories, free from the interference of Earth's atmosphere, have given us some of the most precise and detailed maps of the CMB ever created. The journey began with the Cosmic Background Explorer, or COBE, launched by NASA in 1989. For the first time, COBE provided a clear, full-sky map of the CMB, confirming its existence with undeniable precision. This mission revealed the subtle temperature fluctuations that hinted at the seeds of cosmic structure, earning its team the Nobel Prize in Physics. COBE's success paved the way for even more ambitious projects like the Wilkinson Microwave Anisotropy Probe, or WMAP, which launched in 2001. WMAP took COBE findings to the next level, mapping the CMB with unprecedented resolution. Its data allowed scientists to calculate the universe's age, 13.8 billion years, with remarkable accuracy. WMAP also refined our understanding of the universe's composition, showing that ordinary matter makes up less than 5% of the cosmos, with the rest dominated by dark matter and dark energy. These discoveries were game changers, reshaping our understanding of the universe on the grandest scales. But the story didn't end there. In 2009, the European Space Agency launched the Planck satellite, the most advanced CMB observatory to date. Planck's instruments were so sensitive that they could detect temperature variations as small as 1 part in a million, capturing the CMB's intricate patterns in exquisite detail. This mission not only confirmed earlier findings but also revealed new insights, such as subtle anomalies in the CMB's distribution that continue to puzzle scientists. What made these missions possible were the incredible technological advancements behind them. From ultra-sensitive detectors capable of picking up the faintest signals to sophisticated cooling systems that kept instruments at near absolute zero, these satellites pushed the boundaries of what was possible. They were feats of engineering and ingenuity, designed to capture a signal so ancient and faint that it had traveled for billions of years before reaching us. Yet, studying the CMB is no easy task. The radiation is incredibly weak, and its signal is easily drowned out by other sources of microwave noise, from our own galaxy to even the heat generated by the satellites themselves. Overcoming these challenges required meticulous planning, innovative technology, and a deep understanding of the universe's subtlest signals. The contributions of these missions to cosmology cannot be overstated. They've not only confirmed the Big Bang theory, but also provided a wealth of data that has shaped our understanding of the universe's evolution. From the seeds of galaxies to the mysteries of dark energy, the CMB maps produced by COBE, WMAP, and Planck have become foundational tools for modern astronomy. But even with these incredible achievements, the story of the CMB is far from over. Each new map raises new questions, and each discovery brings us closer to understanding the forces that shaped and continue to shape our universe. As we look to the future, new missions and technologies promise to take us even deeper into the mysteries of this ancient light, revealing secrets we can't yet imagine. Studying the cosmic microwave background is no simple task. Imagine trying to listen to a whisper in a crowded room, except in this case, the whisper is a faint signal from the dawn of the universe, and the crowded room is the entire cosmos. The CMB is incredibly subtle, and isolating it from the noise of other sources of radiation is one of the biggest challenges scientists face. One major obstacle is the Milky Way itself. Our galaxy emits its own microwave radiation, which can easily overwhelm the faint signal of the CMB. To make matters worse, this galactic noise isn't uniform. It varies across the sky, creating a patchwork of interference that scientists must carefully subtract from their data. Think of it like trying to hear a soft melody while standing next to a roaring waterfall. The only way to pick out the music is to filter out the noise, a process that requires precision and patience. Even beyond our galaxy, there are other sources of interference. Dust and gas in the interstellar medium can scatter and absorb microwave radiation, distorting the CMB signal. Then there's the cosmic infrared background, a faint glow from distant galaxies that can also muddy the waters. To make sense of all this, researchers use advanced algorithms and statistical techniques to separate the CMB from these competing signals. It's like piecing together a jigsaw puzzle where half the pieces are from a completely different box. But the challenges don't stop there. The instruments used to study the CMB must be incredibly sensitive, capable of detecting temperature variations as small as 1 part in a million. This level of precision requires cutting-edge technology, including cryogenic cooling systems to keep detectors at near absolute zero. Even the heat generated by the instruments themselves can interfere with readings, so every component must be meticulously designed to minimize noise. Despite these hurdles, the rewards of studying the CMB are immense. By overcoming these challenges, scientists have made groundbreaking discoveries that have reshaped our understanding of the universe. For example, precise measurements of the CMB have allowed us to calculate the universe's age with remarkable accuracy, 13.8 billion years, give or take a few million. They've also revealed the universe's composition, showing that ordinary matter makes up less than 5% of the cosmos, with the rest dominated by dark matter and dark energy. These discoveries weren't just handed to us, they were the result of decades of painstaking work, innovation, and collaboration. From the first faint detection of the CMB by Penzias and Wilson to the exquisitely detailed maps produced by missions like COBE, WMAP, and Planck, each step forward has required a combination of ingenuity, persistence, and a willingness to tackle some of the most daunting challenges in science. And yet, the story of the CMB is far from over. As technology continues to advance, new missions and instruments promise to take our understanding of this ancient light to even greater heights. Each new discovery brings us closer to unraveling the mysteries of the universe, from the nature of dark matter and dark energy to the ultimate fate of the cosmos itself. The challenges may be great, but so too are the rewards, and the journey to uncover them is one of the most exciting adventures in modern science. The story of the cosmic microwave background takes an even more fascinating turn when we consider the theory of cosmic inflation. This idea, first proposed in the early 1980s, suggests that in the first fraction of a second after the Big Bang, the universe didn't just expand, it exploded. Imagine blowing up a balloon to the size of a grapefruit and then, in an instant, inflating it to the size of the entire Earth. That's the kind of exponential growth we're talking about. This rapid expansion, lasting just a tiny fraction of a second, would have stretched the fabric of space itself, smoothing out irregularities and setting the stage for the universe we see today. But how do we know this actually happened? That's where the CMB comes in. The temperature fluctuations we've been talking about, those tiny ripples in the cosmic background, aren't just random. They're incredibly uniform across the sky, with variations so slight that they're almost imperceptible. This uniformity is one of the strongest pieces of evidence for inflation. If the universe had expanded at a slower, more gradual pace, these fluctuations would likely have been much more pronounced and uneven. Instead, the CMB shows a remarkable level of consistency, as if the universe had been stretched so quickly that it didn't have time to develop large irregularities. Think of it like smoothing out a wrinkled bedsheet. If you pull on the sheet slowly, the wrinkles might still linger, but if you yank it with enough force, the fabric becomes almost perfectly flat. Inflation did something similar to the early universe, stretching it so rapidly that any initial irregularities were ironed out, leaving behind the subtle temperature variations we see in the CMB today. The implications of inflation are profound. Not only does it explain the uniformity of the CMB, but it also provides a mechanism for how the universe could have grown from a microscopic point to its current vast scale. Without inflation, it's hard to imagine how the cosmos could have become so large and uniform in such a short amount of time. It's like solving a cosmic puzzle with the CMB as the key piece that fits perfectly into place. But inflation isn't just about solving the past, it also has implications for the future. If the universe expanded so rapidly in its earliest moments, could it happen again? Some theories suggest that inflation might not have been a one-time event but part of a larger cycle, with multiple bangs and expansions happening across an even grander cosmic timeline. While this idea is still speculative, the CMB provides a foundation for testing these theories, offering a glimpse into the universe's deepest origins. And that's not all. The CMB also helps us explore alternative theories about the universe's birth. For example, some scientists have proposed models that don't rely on inflation at all, suggesting instead that the universe might have undergone a slower, more gradual expansion. By studying the precise patterns in the CMB, researchers can compare these theories to the predictions made by inflation, testing which one aligns best with the data. What's remarkable is how much we can learn from this ancient light. It's not just a snapshot of the universe's infancy, it's a testing ground for some of the most profound questions in science. From the rapid expansion of inflation to the possibilities of alternative models, the CMB continues to challenge and inspire, pushing us to rethink our understanding of the cosmos. As we dig deeper into the mysteries of the CMB, we're not just uncovering the universe's past, we're exploring the very nature of existence itself. And with each new discovery, we're reminded that the story of the cosmos is far more complex and far more beautiful than we ever imagined. While the Big Bang theory has become the cornerstone of modern cosmology, it's not the only idea out there. Over the years, scientists have proposed alternative models to explain the universe's origins, each offering a unique perspective on how everything began. One of the most intriguing is the cyclic model, which suggests that the Big Bang wasn't a singular event but part of an endless cycle of expansion and contraction. Imagine the universe as a cosmic accordion, expanding outward before collapsing back in on itself, only to start the process all over again. This theory challenges the idea of a one-time beginning, proposing instead that our universe is just one chapter in an infinite cosmic story. But how does the CMB fit into this picture? The cyclic model predicts that each cycle would leave behind subtle imprints, much like the CMB's temperature fluctuations. However, these patterns would look slightly different from those predicted by the Big Bang theory. By carefully analyzing the CMB's precise measurements, scientists can test whether these predictions hold up. So far, the data has largely supported the Big Bang model, but the cyclic theory remains a compelling alternative, especially as researchers continue to refine their understanding of the CMB's finer details. Then there's the multiverse hypothesis, which takes the idea of multiple universes to a whole new level. This theory suggests that our universe is just one of countless others, each with its own unique properties and physical laws. Some versions of the multiverse idea propose that these universes are constantly colliding or interacting, leaving behind traces in the CMB. For example, certain anomalies in the CMB's temperature distribution have been interpreted as possible evidence of such collisions, though this remains highly speculative. What's fascinating is how the CMB serves as a testing ground for these competing theories. Its precise measurements act like a cosmic ruler, allowing scientists to compare predictions from different models. For instance, the Big Bang theory predicts a specific pattern of temperature fluctuations, while alternative theories like the cyclic model or the multiverse hypothesis might predict slightly different patterns. By scrutinizing the CMB's data, researchers can determine which theories align with the evidence and which ones might need to be rethought. This process of testing and refining theories is at the heart of scientific progress. It's not about proving one idea right and another wrong, but about building a more accurate and complete picture of the universe. The CMB has been instrumental in this effort, providing a wealth of data that has shaped and continues to shape our understanding of the cosmos. Yet, despite the CMB's incredible insights, the debates are far from settled. Some scientists argue that certain anomalies in the CMB's data, like unexpected temperature variations or asymmetries, could hint at phenomena beyond the Big Bang. Others suggest that these anomalies might simply be statistical flukes or the result of measurement errors. The beauty of science is that it thrives on these questions, constantly pushing us to explore new possibilities and challenge our assumptions. As we reflect on the CMB's role in these debates, one thing becomes clear. This ancient light is more than just a relic of the past. It's a living record of the universe's origins, a tool for testing ideas, and a source of endless fascination. Whether it's supporting the Big Bang theory, challenging it, or opening the door to entirely new possibilities, the CMB continues to shape our understanding of the cosmos in profound and unexpected ways. And as we look to the future, the questions raised by the CMB remind us that science is a journey, not a destination. Each discovery leads to new mysteries, each answer sparks new questions, and each theory brings us closer to understanding the universe's deepest secrets. The CMB isn't just a window into the past, it's a guide to the future, pointing the way toward discoveries we can't yet imagine. One of the most astonishing achievements in modern cosmology is the ability to determine the universe's age with extraordinary precision, and it's all thanks to the cosmic microwave background. This ancient light, a relic from the universe's infancy, acts like a cosmic clock, allowing scientists to calculate how long it's been since the Big Bang. The number they've landed on, 13.8 billion years. But how exactly do we arrive at such a precise figure? The answer lies in the intricate dance between the universe's expansion and its composition, both of which are encoded in the CMB. To understand how this works, let's start with the universe's expansion. When scientists measure the CMB, they're essentially looking at a snapshot of the universe when it was just 380,000 years old. But this snapshot doesn't just show us what the universe looked like back then. It also reveals how fast it was expanding. By studying the subtle fluctuations in the CMB's temperature, researchers can trace the rate of expansion over billions of years, much like rewinding a cosmic film. This rate, known as the Hubble constant, is a crucial piece of the puzzle, but the expansion rate alone isn't enough to determine the universe's age. We also need to know how much matter and energy the universe contains. This is where the CMB's density measurements come into play. The temperature patterns in the CMB reveal the distribution of matter and energy in the early universe, which in turn tells us how much gravitational pull there was to slow down the expansion. By combining these two pieces of information, the expansion rate and the density of matter, scientists can calculate the universe's age with remarkable accuracy. What's truly remarkable about this process is the level of precision it allows. Thanks to missions like WMAP and Planck, which mapped the CMB in exquisite detail, we now know the universe's age to within a fraction of a percent. That's like being able to pinpoint the exact moment a single candle was lit in a room full of billions. Knowing the universe's age isn't just a matter of satisfying curiosity, it's a cornerstone of cosmology. It gives us a timeline for the formation of galaxies, stars, and planets, and it helps us understand how the universe has evolved over billions of years. It's also a critical piece of evidence for the Big Bang theory itself. If the universe were significantly older or younger, it would challenge our understanding of its origins and evolution. But the CMB doesn't just tell us when the universe began, it also reveals what it's made of. By analyzing the CMB's temperature fluctuations, scientists can determine the proportions of ordinary matter, dark matter, and dark energy that make up the cosmos. This information is like a cosmic ingredient list showing us the recipe for everything we see and don't see in the universe. For example, the CMB tells us that ordinary matter, the stuff that makes up stars, planets, and even us, accounts for less than 5% of the universe's total content. The rest is a mysterious mix of dark matter and dark energy, two invisible forces that shape the cosmos on the grandest scales. Without the CMB, we wouldn't have this detailed understanding of the universe's composition, and we'd be left in the dark, literally, about the forces that govern its behavior. The CMB is more than just a relic of the past. It's a tool for understanding the universe's present and future. By decoding its patterns, we're not just uncovering the story of how everything began, we're piecing together the blueprint of the cosmos itself. And as we'll see, this ancient light continues to illuminate some of the most profound mysteries in science, from the nature of dark energy to the ultimate fate of the universe. The cosmic microwave background isn't just a relic of the universe's birth. It's also a cosmic ledger, a detailed record of what the universe is made of. What we've learned from this ancient light is nothing short of astonishing. The universe we see around us, filled with stars, planets, and galaxies, accounts for less than 5% of everything that exists. The rest, it's a mysterious mix of dark matter and dark energy, two invisible forces that dominate the cosmos. But how do we know this? The answer lies in the subtle patterns and fluctuations encoded in the CMB. Let's start with ordinary matter, the stuff we're most familiar with. This includes everything from the atoms in our bodies to the gas and dust in distant galaxies. While it might seem like ordinary matter is the main ingredient of the universe, the CMB reveals that it's actually just a small fraction, making up less than 5% of the total cosmic pie. This matter plays a crucial role in forming stars, planets, and life as we know it, but it's far from the whole story. Then there's dark matter, an invisible substance that makes up roughly 27% of the universe. Unlike ordinary matter, dark matter doesn't interact with light or electromagnetic forces, which means we can't see it directly, but we know it's there because of its gravitational effects. The CMB's temperature fluctuations show how dark matter's gravitational pull influenced the early universe, guiding the formation of galaxies and galaxy clusters. Without dark matter, the universe as we know it simply wouldn't exist. It's the cosmic scaffolding that holds everything together. But the most mysterious ingredient of all is dark energy, which makes up a staggering 68% of the universe. Unlike dark matter, which pulls things together, dark energy pushes them apart, driving the accelerated expansion of the universe. The CMB provides some of the strongest evidence for dark energy's existence, showing how it has shaped the universe's structure over billions of years. By studying the way the CMB's light has stretched as the universe expanded, scientists can trace the influence of this mysterious force, revealing its dominance in the cosmic landscape. So, how does the CMB help us determine these proportions? It all comes down to the patterns in its temperature fluctuations and polarization. These tiny variations act like a cosmic fingerprint, encoding information about the universe's composition. For example, the size and distribution of the fluctuations reveal how much matter, both ordinary and dark, was present in the early universe. Meanwhile, the way the CMB's light has been stretched over time provides clues about the role of dark energy. By analyzing these patterns with incredible precision, scientists can piece together the recipe for the universe, revealing the proportions of its key ingredients. This composition has profound implications for our understanding of the cosmos. It tells us that the universe we see is just the tip of the iceberg, with the vast majority of its content hidden from view. It also raises fascinating questions about the nature of dark matter and dark energy, two of the biggest mysteries in modern science. What is dark matter made of? Why does dark energy dominate the universe? These are questions that continue to drive scientific exploration, and the CMB is one of our most powerful tools for finding answers. But the CMB doesn't just tell us what the universe is made of, it also reveals its shape. The geometry of the universe, whether it's flat, curved, or something else entirely, is another piece of the puzzle encoded in this ancient light. By studying the CMB's patterns, scientists can measure the universe's curvature, providing insights into its overall structure and evolution. And as we'll see, this cosmic geometry is just as fascinating and just as mysterious as the universe's composition. When we think about the universe's shape, it's easy to imagine it as some vast, mysterious structure, curved, twisted, or perhaps even infinite. But what if the universe isn't as complicated as it seems? What if, on the largest scales, it's as simple and straightforward as a flat sheet of paper? This might sound surprising, but that's exactly what the cosmic microwave background tells us. The CMB provides some of the strongest evidence that the universe is flat, meaning it follows the rules of Euclidean geometry, the same geometry we learn in school. But what does it mean for the universe to be flat? In everyday terms, think of a flat sheet of paper. If you draw a triangle on it, the angles add up to 180 degrees and parallel lines never meet. Now imagine that same flatness but on a cosmic scale. The universe, when viewed as a whole, behaves the same way. Light travels in straight lines, and the angles of triangles formed by galaxies or other large structures follow the rules of flat geometry. This flatness is a crucial piece of the puzzle, and it's something scientists have been able to confirm by studying the CMB's temperature fluctuations. The CMB's patterns act like a cosmic ruler, allowing us to measure the universe's curvature. If the universe were curved, like the surface of a sphere or a saddle, those patterns would look different. For example, in a spherical universe, the fluctuations would appear larger and more spread out, while in a saddle-shaped universe, they'd look smaller and more compressed. But the CMB shows none of these distortions. Instead, its temperature variations align perfectly with what we'd expect from a flat universe. This discovery has profound implications for cosmology. A flat universe supports the theory of cosmic inflation, which suggests that the early universe expanded so rapidly that any initial curvature was stretched out, leaving the cosmos flat on large scales. It's like taking a crumpled piece of paper and smoothing it out. No matter how wrinkled it started, the rapid expansion would have flattened it completely. This alignment between inflation and the universe's geometry is one of the most compelling pieces of evidence for the theory, and it's all thanks to the CMB. But the CMB doesn't just tell us about the universe's shape, it also reveals something even more subtle: its polarization. Just as light can be polarized by reflecting off a surface, the CMB's light carries a faint imprint of polarization, a kind of directional fingerprint left over from the early universe. This polarization isn't just a curiosity, it's a treasure trove of information, offering clues about everything from the first moments after the Big Bang to the behavior of cosmic structures. The CMB's polarization patterns are like ripples on the surface of a pond, carrying echoes of the forces that created them. By studying these patterns, scientists can probe the universe's earliest moments, testing theories about inflation, dark matter, and even the nature of gravity itself. It's a reminder that the CMB isn't just a static image of the past, it's a dynamic, living record, full of secrets waiting to be uncovered. What's truly remarkable is how much we've learned from this ancient light. It's not just a relic of the Big Bang, it's a guide to the universe's structure, its origins, and its future. From the flatness of space to the subtle ripples of polarization, the CMB continues to illuminate some of the deepest mysteries in science, reminding us that even the faintest whispers can carry the loudest truth. And as we'll see, the story of this cosmic fingerprint is far from over. It's just beginning to reveal its secrets. The cosmic microwave background isn't just a map of temperature fluctuations, it's also a treasure trove of hidden details encoded in its polarization. To understand what polarization means, think of light as a wave. Normally, light waves vibrate in all directions, but when they become polarized, those vibrations align in a specific orientation. It's like taking a tangled bundle of strings and straightening them out so they all point in the same direction. This alignment happens when light interacts with matter or is influenced by gravitational effects, and it leaves a subtle imprint on the light's properties. In the case of the CMB, this polarization carries a wealth of information about the early universe. When the CMB was first released, roughly 380,000 years after the Big Bang, the light didn't just travel freely, it also interacted with the charged particles and gravitational fields of the early cosmos. These interactions left behind a faint but detectable polarization pattern, like a cosmic fingerprint etched into the light itself. What makes this polarization so valuable is that it tells us more than just the temperature of the early universe. It reveals the dynamics of that era, the movements, forces, and processes that shaped the cosmos in its infancy. For example, the CMB's polarization patterns can provide clues about cosmic inflation, the rapid expansion that occurred just moments after the Big Bang. During inflation, the universe would have been filled with gravitational waves, ripples in spacetime itself. These waves would have left a distinct signature in the CMB's polarization, creating swirling patterns known as B-mode polarization. Detecting these patterns is like finding the smoking gun of inflation, offering direct evidence of this pivotal moment in the universe's history. But polarization doesn't just tell us about inflation. It also sheds light on the formation of the universe's first structures. As the early universe expanded and cooled, regions of slightly higher density began to collapse under their own gravity, forming the seeds of galaxies and galaxy clusters. These collapsing regions would have created their own gravitational fields, which in turn influenced the polarization of the CMB. By studying these patterns, scientists can trace how the first structures began to take shape, revealing the processes that led to the cosmos we see today. One of the most exciting aspects of CMB polarization research is how it pushes the boundaries of what we can observe. While temperature fluctuations give us a broad picture of the early universe, polarization offers a finer level of detail, like zooming in on a cosmic photograph to see the brushstrokes. This has led to a new generation of experiments designed specifically to measure the CMB's polarization with unprecedented precision. Instruments like the Simons Observatory and the CMB S4 project are at the forefront of this effort, using advanced detectors and cutting-edge technology to map these subtle patterns across the sky. These missions aren't just about refining our understanding of the past, they are also about exploring the universe's most fundamental questions. For instance, the search for B-mode polarization could confirm the existence of primordial gravitational waves, offering a direct window into the universe's first moments. It could also provide insights into the nature of dark energy and the forces driving the universe's expansion. The story of the CMB's polarization is still being written, with each new discovery adding another piece to the puzzle. It's a reminder that even the faintest signals can carry profound meaning, and that the universe's oldest light still has secrets to share. As we continue to study these patterns, we're not just uncovering the history of the cosmos, we're exploring the very forces that shaped it and the mysteries that still lie ahead. Gravitational waves are one of the most fascinating predictions of modern physics. Ripples in the fabric of spacetime itself, created by some of the most violent and energetic events in the universe. But what if I told you that these waves aren't just a product of colliding black holes or neutron stars? They might also hold the key to understanding the universe's very first moments. This is where primordial gravitational waves come in, an echo from the dawn of time, when the universe was just a fraction of a second old. According to the theory of cosmic inflation, the universe underwent an unimaginably rapid expansion in its earliest moments, stretching faster than the speed of light. This explosive growth would have sent ripples through spacetime, much like tossing a stone into a pond. These ripples, known as primordial gravitational waves, would have left a unique imprint on the cosmic microwave background, specifically in its polarization patterns. Here's how it works. As these gravitational waves traveled through the early universe, they would have caused tiny distortions in the CMB's light, creating a distinctive swirling pattern known as B-mode polarization. Think of it like the ripples on the surface of a lake, but on a cosmic scale. Detecting this pattern would be like finding a fingerprint from the Big Bang itself, offering direct evidence that inflation really happened. But finding this signal is no easy task. The B-mode polarization patterns are incredibly faint, buried beneath a sea of other signals and noise. To make matters worse, there are other sources of B-modes, like dust in our own galaxy or gravitational lensing from distant galaxies, that can mimic the signature of primordial gravitational waves. Separating these signals requires painstaking precision and cutting-edge technology. That's where ambitious projects like the Simons Observatory and the CMB S4 come in. These next-generation experiments are designed to measure the CMB's polarization with unprecedented sensitivity, searching for the telltale signs of primordial gravitational waves. Using arrays of ultra-sensitive detectors and advanced data analysis techniques, these missions aim to peel back the layers of interference and reveal the faint whisper of the universe's birth. What makes this search so exciting is what it could tell us. If we detect these primordial gravitational waves, it wouldn't just confirm inflation. It would give us a direct window into the physics of the early universe, revealing energies and conditions far beyond anything we can recreate in a lab. It could also help us understand the nature of gravity itself and how it behaves on the tiniest scales. But even if we don't find this signal, the search itself is transformative. It pushes the boundaries of what we can observe and challenges us to refine our theories and technologies. The CMB, in this sense, isn't just a relic of the past, it's a bridge to the future, connecting the universe's earliest moments to the questions we're still trying to answer today. As we continue to explore the CMB's polarization, we're not just looking for answers about the past. We're uncovering the tools to understand the universe's evolution, from its fiery birth to the vast, interconnected web of galaxies we see today. And in doing so, we're reminded that the story of the cosmos is still being written, with each discovery bringing us closer to understanding the forces that shaped it and the mysteries that still lie ahead. The cosmic microwave background isn't just a window into the universe's past, it's also a crystal ball, offering clues about its ultimate fate. By studying this ancient light, scientists can peer into the distant future, exploring scenarios that range from a cosmic freeze to a dramatic collapse or even a violent rip. These possibilities, shaped by the interplay of dark energy and the universe's expansion, are encoded in the very fabric of the CMB, waiting to be decoded. Let's start with the most widely accepted scenario, the Big Freeze. This theory suggests that as dark energy continues to drive the universe's accelerating expansion, galaxies will drift farther and farther apart. Over trillions of years, the cosmos will grow colder and darker, with stars burning out and matter becoming increasingly sparse. It's a quiet, almost poetic end, a universe that fades into stillness like embers cooling after a fire. The CMB plays a key role in predicting this outcome. By measuring the universe's expansion rate and the amount of dark energy through the CMB's temperature fluctuations, scientists can calculate how quickly the universe is stretching and how far it will go. The data so far points to an ever-expanding cosmos, making the Big Freeze the most likely scenario. But what if the universe doesn't keep expanding forever? Enter the Big Crunch, a dramatic alternative where the universe's expansion slows, stops, and eventually reverses. In this scenario, dark energy loses its dominance and gravity takes over, pulling everything back together in a cosmic collapse. Galaxies, stars, and even atoms would be crushed into an infinitely dense point, a mirror image of the Big Bang. While this idea might seem like science fiction, the CMB allows us to test its plausibility. By analyzing the universe's curvature and the balance between dark energy and gravity, scientists can assess whether a big crunch is possible. So far, the evidence suggests it's unlikely, but the CMB's precise measurements keep the door open to new possibilities. Then there's the Big Rip, a scenario as dramatic as it sounds. In this model, dark energy doesn't just accelerate the universe's expansion, it intensifies over time, eventually tearing apart galaxies, stars, and even atoms. It's a violent, cataclysmic end where the fabric of spacetime itself is ripped apart. While this might sound like the plot of a sci-fi thriller, it's a real theoretical possibility, and one that the CMB helps us explore. By measuring the properties of dark energy through the CMB's temperature and polarization patterns, scientists can test whether this force could grow strong enough to cause a big rip. While current data doesn't strongly support this idea, the CMB's ability to refine our understanding of dark energy keeps the question alive. What's fascinating is how the CMB doesn't just inform these predictions, it also connects them to the universe's earliest moments. The same light that carries clues about dark energy and expansion also holds secrets about the forces that shaped the cosmos in its infancy. This duality makes the CMB a bridge between the past and the future, a tool for exploring both where we came from and where we're headed. But the CMB's role doesn't stop at predicting the universe's fate. It also serves as a laboratory for testing the fundamental laws of physics. For example, the subtle patterns in the CMB's polarization can reveal whether gravity behaves differently on cosmic scales than it does here on Earth. They can also provide insights into the nature of spacetime itself, probing questions that go beyond our current understanding of physics. As we continue to study the CMB, we're not just uncovering the universe's past, we're exploring the forces that will shape its future. From the quiet fade of the Big Freeze to the dramatic collapse of the Big Crunch or the explosive end of the Big Rip, the CMB offers a glimpse into the cosmos's ultimate destiny. And in doing so, it reminds us that the story of the universe is far from over. It's a tale still being written, with each discovery bringing us closer to understanding the grand narrative of existence. The cosmic microwave background isn't just a snapshot of the universe's infancy, it's also a cosmic laboratory, a place where we can test the laws of physics under conditions far beyond anything we can recreate on Earth. Imagine a time when the universe was a seething cauldron of energy. Temperatures soared to trillions of degrees, and the fundamental forces of nature were unified into a single, incomprehensible force. This is the realm the CMB allows us to explore, offering a window into the extreme conditions that shape the cosmos and the fundamental laws that govern it. One of the most profound ways the CMB tests our understanding of physics is through its connection to particle physics. In the early universe, particles and energy existed in a state of constant interaction, governed by forces we're still working to understand. By studying the CMB's temperature fluctuations, scientists can probe the behavior of particles at energies far beyond what any particle accelerator on Earth can produce. For example, the CMB provides clues about the existence of hypothetical particles like actions or sterile neutrinos, which could explain some of the mysteries of dark matter. It's like having a time machine that lets us peer back into a universe where the rules of particle physics were being written. But the CMB doesn't just test particle physics, it also challenges our understanding of quantum mechanics. In the early universe, quantum fluctuations on the tiniest scales were stretched to cosmic proportions by inflation, leaving behind the temperature variations we see in the CMB today. This connection between the quantum world and the cosmic scale is one of the most fascinating aspects of modern physics, and the CMB is one of the few places where we can observe it in action. By analyzing these fluctuations, scientists can test theories about quantum gravity, the nature of spacetime, and even the possibility of multiple universes. Then there's general relativity, Einstein's groundbreaking theory of gravity, which the CMB has repeatedly confirmed on cosmic scales. The way light from the CMB bends around massive objects, a phenomenon known as gravitational lensing, provides direct evidence of how gravity warps spacetime. But the CMB also pushes the boundaries of general relativity, testing whether it holds up under the extreme conditions of the early universe. For example, some theories suggest that gravity might behave differently at very high energies or on very large scales, and the CMB offers a unique way to test these ideas. Perhaps most exciting is the potential for the CMB to reveal new physics beyond the standard model, the framework that describes the fundamental particles and forces we know of. The standard model has been incredibly successful, but it leaves many questions unanswered, like the nature of dark matter and dark energy, or why the universe has more matter than antimatter. The CMB's precise measurements could hold clues to these mysteries, pointing the way to new theories and discoveries. For instance, anomalies in the CMB's temperature distribution or polarization patterns might hint at new particles, forces, or even dimensions we haven't yet imagined. Beyond its scientific significance, the CMB also carries a deep cultural and philosophical weight. It's a reminder of our place in the cosmos, a universe that began with a big bang, expanded over billions of years, and gave rise to stars, planets, and life. The CMB connects us to the universe's earliest moments, offering a glimpse of the forces that shaped everything we see around us. It's a humbling and awe-inspiring story, one that challenges us to think about the nature of existence, the origins of the cosmos, and our role in this vast, interconnected web of life. In many ways, the CMB is more than just a scientific tool. It's a bridge between the past and the future, between the known and the unknown. It invites us to explore the universe's deepest mysteries, to question our assumptions, and to dream of discoveries that lie just beyond the horizon. And as we continue to study this ancient light, we're not just uncovering the secrets of the cosmos, we're uncovering the story of ourselves and the forces that brought us into being. So, the next time you hear about the cosmic microwave background, remember this. It's not just a faint glow from the distant past. It's a laboratory, a time machine, and a guide to the universe's most profound questions. And as we'll see, the journey to understand this ancient light is far from over. It's only just beginning. The cosmic microwave background isn't just a scientific discovery. It's a testament to humanity's insatiable curiosity, our relentless drive to understand the universe and our place within it. This ancient light, a faint whisper from the dawn of time, reminds us that the cosmos isn't just something out there, distant and unknowable. It's a story we're part of, one that began billions of years before our species even existed. And in studying the CMB, we're not just exploring the universe, we're connecting with it on a profoundly human level. As Carl Sagan once said, somewhere, something incredible is waiting to be known. The CMB embodies that idea. It's a cosmic puzzle, a mystery that has captivated scientists and thinkers for decades, and it represents the very essence of scientific exploration. It's not just about collecting data or testing theories. It's about seeking answers to questions that have haunted us since the dawn of civilization. Where did we come from? Why are we here? What lies beyond the stars? The CMB doesn't just provide clues to these questions, it invites us to ask them in the first place. What's remarkable is how this ancient light bridges the gap between the scientific and the deeply personal. When we look at the CMB, we're not just seeing a map of temperature fluctuations, we're seeing the echoes of the universe's birth, a moment that set in motion everything we know and love. It's a reminder that the atoms in our bodies, the stars above us, and the galaxies stretching into infinity all share a common origin. In that sense, the CMB connects us to the cosmos in a way that's almost poetic. As the physicist Brian Greene put it, we are the universe's way of knowing itself. This connection goes beyond science. It taps into something universal, a shared sense of wonder that transcends cultures, languages, and time. The CMB inspires awe because it reminds us of how vast and mysterious the universe truly is. It challenges us to think bigger, to dream beyond the confines of our daily lives, and to imagine a reality far greater than anything we've ever known. And yet, it also grounds us, showing us that we're part of something larger, a cosmic tapestry woven from the threads of time and space. But the story of the CMB isn't just about looking back, it's also about looking forward. As we continue to study this ancient light, we're not just uncovering the universe's past, we're shaping its future. New missions and technologies promise to take our understanding of the CMB to even greater heights, pushing the boundaries of what we can observe and explore. Projects like the Simons Observatory and CMB-S4 are poised to revolutionize our understanding of the cosmos, offering insights into everything from the nature of dark energy to the origins of the universe itself. The future of CMB research is as exciting as it is uncertain. What new discoveries lie hidden in its faint signals? What mysteries will it help us unravel? These are questions that drive scientists and dreamers alike, fueling a quest that's as much about curiosity as it is about knowledge. And as we move forward, one thing is clear: the CMB will continue to inspire, to challenge, and to connect us to the cosmos in ways we're only beginning to imagine. In the end, the cosmic microwave background isn't just a relic of the universe's birth. It's a mirror reflecting humanity's deepest questions and aspirations. It's a reminder that the pursuit of knowledge isn't just about finding answers. It's about embracing the journey, the wonder, and the endless possibilities that lie ahead. And as we continue to explore this ancient light, we're not just uncovering the secrets of the universe, we're discovering what it means to be human in a vast and mysterious cosmos. The story of the cosmic microwave background is far from over. In fact, it's entering an exciting new chapter, one that promises to push the boundaries of our understanding even further. Across the globe, ambitious new missions and experiments are being developed to study the CMB with unprecedented precision, aiming to uncover secrets that have eluded us for decades. These projects aren't just about refining what we already know. They're about opening doors to discoveries that could redefine our understanding of the universe. At the forefront of this effort is the Simons Observatory, a state-of-the-art facility located in Chile's Atacama Desert. With its array of powerful telescopes and ultra-sensitive detectors, this observatory is designed to map the CMB's temperature and polarization with incredible detail. One of its primary goals is to search for the faint signatures of primordial gravitational waves, ripples in spacetime from the universe's first moments. Detecting these waves would be a monumental achievement, offering direct evidence of cosmic inflation and shedding light on the physics of the early universe. But the Simons Observatory isn't stopping there. It's also poised to refine our understanding of dark energy, the mysterious force driving the universe's accelerated expansion, by measuring the CMB's subtle distortions with unparalleled accuracy. Meanwhile, the CMB S4 project is gearing up to take CMB research to even greater heights. This next-generation experiment will deploy an extensive network of telescopes across multiple sites, creating a comprehensive map of the CMB's polarization patterns. By combining data from these instruments, CMB S4 aims to achieve a level of precision that could reveal new insights into the universe's composition, its expansion history, and the nature of dark matter. One of its most intriguing possibilities is the potential to detect anomalies in the CMB that could hint at new physics beyond the standard model, perhaps even evidence of extra dimensions or exotic particles. What makes these missions so exciting isn't just the technology they're using, but the questions they're trying to answer. For instance, how did the universe transition from a hot, dense state to the vast, structured cosmos we see today? What role did dark matter play in shaping the universe's first structures? And how has dark energy influenced the universe's expansion over billions of years? The answers to these questions could be hiding in the CMB's faint whispers, waiting to be uncovered by these cutting-edge experiments. But the significance of these missions goes beyond the science. They represent the culmination of decades of progress, a testament to humanity's ingenuity and determination to understand the cosmos. From the accidental discovery of the CMB by Penzias and Wilson to the exquisitely detailed maps produced by Kobe, WMAP, and Planck, each step forward has brought us closer to unraveling the universe's deepest mysteries. Now, with projects like the Simons Observatory and CMB S4, we're on the verge of another leap, one that could transform our understanding of the universe's origins and its ultimate fate. Yet, even as we prepare for these groundbreaking missions, the CMB continues to remind us of how much we still don't know. Despite decades of study, This ancient light remains full of mysteries, from the subtle anomalies in its temperature distribution to the faint ripples of polarization that could hold clues to the universe's first moments. These lingering questions aren't just challenges, they're opportunities, invitations to explore the unknown and to push the boundaries of what we thought was possible. As we look to the future, one thing is clear: the CMB is more than just a relic of the past. It's a living, dynamic record of the universe's history, a guide to its structure, and a window into its future. And with each new mission, each new discovery, we're not just uncovering the secrets of the cosmos, we're rewriting the story of our place within it. The journey to understand the CMB is far from over, and the next chapter promises to be the most exciting yet. For all the groundbreaking insights the cosmic microwave background has given us, it's far from giving up all its secrets. In fact, some of the most profound questions in cosmology remain unanswered, and the CMB is at the heart of the quest to solve them. What is the true nature of dark matter and dark energy, those invisible forces that dominate the universe? How exactly did cosmic inflation work, and what triggered it? And could there be other universes out there, part of a vast multiverse? These aren't just abstract ideas, they're the driving force behind some of the most ambitious research in science today. Let's start with dark matter, the mysterious substance that makes up about 27% of the universe. We know it's there because of its gravitational effects, but we've yet to directly detect it. The CMB offers some of the best clues we have, revealing how dark matter's gravitational pull shaped the early universe. Yet, its true nature, whether it's made of exotic particles or something even stranger, remains one of the biggest puzzles in physics. Solving this mystery wouldn't just fill in a gap in our understanding. It could revolutionize particle physics and reshape our view of the cosmos. Then there's dark energy, the enigmatic force driving the universe's accelerated expansion. The CMB has given us compelling evidence for its existence, but we still don't know what it is. Is it a property of space itself, as Einstein's cosmological constant suggests? Or is it something entirely new, a force that might change over time? These questions aren't just academic, they're tied to the ultimate fate of the universe. Will the cosmos continue to expand forever, or could dark energy eventually reverse its effects? The CMB is our best tool for exploring these possibilities, offering a glimpse into the forces that will shape the universe's destiny. And then there's inflation, the rapid expansion that occurred in the universe's first moments. While the CMB provides strong evidence for inflation, the exact mechanism behind it remains a mystery. What caused the universe to expand so dramatically? Was it a single event or part of a larger cycle? Some theories even suggest that inflation could have created a multiverse, where our universe is just one of countless others, each with its own unique laws of physics. The CMB's subtle patterns and anomalies could hold the key to answering these questions, offering clues about the universe's earliest moments and the possibility of other realities beyond our own. What's fascinating is how these mysteries aren't just isolated questions, they're deeply interconnected. Understanding dark matter could shed light on the nature of dark energy. Deciphering inflation could reveal whether a multiverse exists, and all of these discoveries could reshape our understanding of the fundamental laws of physics. The CMB is the thread that ties these questions together, a cosmic Rosetta Stone that helps us decode the universe's deepest secrets. But the implications of CMB research go beyond science. These discoveries challenge us to think about our place in the cosmos, to imagine realities far beyond our own, and to confront the limits of human knowledge. They remind us that the universe is far stranger and more complex than we ever imagined, full of mysteries that inspire awe and wonder. As we continue to study the CMB, we're not just uncovering the universe's past, we're exploring the very fabric of reality itself. Each new discovery brings us closer to answering some of the most profound questions in science, while opening the door to new mysteries we've yet to imagine. The journey to understand the CMB is far from over, and the next chapter promises to be the most exciting yet. What does the cosmic microwave background have to do with the search for life beyond Earth? At first glance, it might seem like these two topics are worlds apart. One deals with the universe's earliest moments, while the other focuses on the possibility of life elsewhere. But when we look closer, the connection becomes clear. The CMB isn't just a relic of the Big Bang, it's a key to understanding the conditions that make life possible, both in our corner of the cosmos and potentially in others. To begin, let's think about what life needs to exist. At its core, life as we know it requires a few basic ingredients: a stable environment, the right chemical elements, and enough time for complex molecules to form and evolve. These conditions don't just happen by chance, they are shaped by the universe's structure, its expansion, and even the forces that govern it, and that's where the CMB comes in. By revealing the universe's age, composition, and evolution, the CMB helps us understand the cosmic stage on which life could potentially emerge. For example, the CMB tells us that the universe is 13.8 billion years old. That might seem like a random number, but it's actually critical for life. It takes time for stars to form, for those stars to create heavier elements like carbon and oxygen, and for planets to coalesce around those stars. A younger universe might not have had enough time for these processes to unfold, while an older one might have seen its stars burn out long ago. The CMB's precise measurement of the universe's age gives us a timeline for when and where life could arise. But it's not just about time, it's also about the universe's composition. The CMB reveals that ordinary matter, the stuff that makes up planets, stars, and living things, accounts for less than 5% of the universe's total content. The rest is dark matter and dark energy, two invisible forces that shape the cosmos on the largest scales. While we don't yet fully understand these forces, we know they play a crucial role in creating the conditions for life. Dark matter's gravitational pull helps galaxies form, while dark energy drives the universe's expansion, creating the vast, interconnected web of galaxies we see today. Without these forces, the universe might have been too chaotic or too sparse for life to take hold. The CMB also gives us insights into the universe's habitability on smaller scales. For instance, the temperature fluctuations in the CMB tell us about the early seeds of structure, the tiny ripples that would one day grow into galaxies and galaxy clusters. These structures are essential for life because they provide the environments where stars and planets can form. Without them, the universe would be a featureless void, devoid of the complex systems that make life possible. What's fascinating is how the CMB connects the universe's largest scales to the smallest details of habitability. It's like a cosmic blueprint, showing us how the Big Bang set the stage for the emergence of galaxies, stars, and planets, and ultimately life itself. By studying the CMB, we're not just learning about the universe's origins, we're uncovering the conditions that make life possible, both here and potentially elsewhere. This connection raises an intriguing question. Could the CMB help us identify other habitable regions in the universe? While the CMB itself doesn't point us to specific planets or star systems, it does provide a framework for understanding where life might be most likely to arise. For example, regions with a higher density of galaxies might offer more opportunities for life to develop, while areas dominated by dark energy's rapid expansion could be too sparse. By mapping the universe's structure and evolution, the CMB helps us narrow down the search for life, guiding us toward the most promising corners of the cosmos. But the CMB's role in the search for life goes beyond just the physical conditions. It also shapes our perspective, reminding us of our place in the universe. When we look at the CMB, we're seeing the universe as it was just 380,000 years after the Big Bang, a time when stars, planets, and life were still billions of years away. It's a humbling reminder of how young we are in the grand scheme of things and how much of the universe's story is still unfolding. This perspective is crucial as we search for life beyond Earth. It reminds us that we're part of a much larger cosmic narrative, one that began long before us and will continue long after. The CMB isn't just a scientific tool, it's a lens through which we can explore the universe's potential for life and our own place within it. As we continue to study this ancient light, we're not just uncovering the secrets of the cosmos, we're also asking profound questions about what it means to be alive in a vast and mysterious universe. Whether or not we find life elsewhere, the CMB reminds us that the universe is full of possibilities, and that the search for life is as much about understanding ourselves as it is about exploring the stars. The cosmic microwave background is more than a scientific marvel, it's a profound reminder of our place in the universe. When we look at this ancient light, we're not just observing a moment frozen in time, we're witnessing the very origins of the cosmos itself. It's a humbling experience, one that places our existence in perspective. Against the backdrop of a universe that's 13.8 billion years old, our lives and even our entire species are just a fleeting blip in the grand cosmic timeline. Yet, in that fleeting moment, we've managed to uncover one of the universe's greatest secrets. This realization can evoke a deep sense of humility. The CMB shows us that the universe is vast, complex, and often beyond our comprehension. It challenges us to acknowledge how much we don't know, while also celebrating how much we've learned. In a way, the CMB is a cosmic mirror, reflecting not just the universe's beginnings but also our own journey of discovery. It reminds us that science isn't just about finding answers, it's about asking questions, about staying curious even when the answers seem out of reach. At the same time, the CMB inspires a sense of connection. Every atom in our bodies, every star in the sky, and every galaxy stretching into infinity can trace its origins back to the same fiery moment captured in the CMB. We're not just observers of the universe, we're part of it, woven into its very fabric. This connection goes beyond science. It taps into something deeply human, a shared sense of wonder that transcends cultures, languages, and time. What's remarkable is how the CMB bridges the gap between the cosmic and the personal. It's easy to feel small when confronted with the universe's immensity, but the CMB also shows us that even the smallest things, like a faint whisper of light, can carry profound meaning. In unlocking the secrets of the CMB, we've gained insights into the universe's age, its composition, and its evolution. We've learned about the seeds of galaxies, the invisible forces of dark matter and dark energy, and the rapid expansion that shaped the cosmos in its earliest moments. These discoveries aren't just scientific achievements, they're milestones in our understanding of existence itself. As we reflect on the CMB's significance, it's worth considering how this ancient light continues to shape our perspective. It reminds us that the universe is more than a collection of stars and galaxies. It's a story, one that began with the Big Bang and continues to unfold with every passing moment. We're not just passive observers of this story, we're active participants using the tools of science to explore, question, and learn. The CMB invites us to embrace both our smallness and our significance. It shows us that while we may be tiny in the grand scheme of things, our curiosity and ingenuity have allowed us to uncover some of the universe's deepest mysteries. In doing so, we've connected ourselves to a narrative that spans billions of years, one that's still being written. And as we continue to explore the cosmos, we're not just uncovering its secrets, we're discovering what it means to be human in a vast and mysterious universe. So, the next time you look up at the night sky, remember this: the faint glow of the CMB is more than just a scientific curiosity. It's a reminder of where we came from, a guide to where we're going, and a testament to the enduring power of curiosity. In the end, the CMB isn't just a window into the universe, it's a window into ourselves and the endless possibilities that lie ahead. What do we really know about the universe, and how did we get here? Over the course of this video, we've explored the cosmic microwave background, a faint whisper of light that carries the story of the cosmos itself. But what have we learned from this ancient glow? The CMB isn't just a relic of the Big Bang. It's a treasure trove of insights that have reshaped our understanding of the universe. From its age and composition to its structure and evolution, the CMB has given us answers to some of the biggest questions in science and raised new ones that continue to drive discovery. One of the most profound lessons from the CMB is the universe's age. Thanks to precise measurements of this ancient light, we now know the cosmos is approximately 13.8 billion years old. That number isn't just a milestone, it's a timeline, a way to trace the universe's history from its fiery birth to the vast, interconnected web of galaxies we see today. By studying the CMB, we've been able to piece together the story of how stars, planets, and even life came to be, giving us a deeper appreciation for the cosmic processes that made our existence possible. But the CMB doesn't just tell us how old the universe is, it also reveals what it's made of. Ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos. The rest is a mysterious mix of dark matter and dark energy, two invisible forces that shape the universe on the grandest scales. Dark matter acts as cosmic scaffolding, holding galaxies together, while dark energy drives the universe's accelerated expansion. Without the CMB, we wouldn't have this detailed understanding of the universe's composition, and we'd be left in the dark, quite literally, about the forces that govern it. The CMB has also transformed our understanding of the universe's structure. Those tiny temperature fluctuations we've talked about, they're the seeds of cosmic architecture, the subtle ripples that grew into galaxies, clusters, and the vast cosmic web. By mapping these patterns, scientists can trace the universe's evolution over billions of years, from its fiery beginnings to the intricate structures we see today. The CMB isn't just a snapshot of the past, it's a blueprint for the universe's growth, offering a window into how everything we see came to be. Perhaps most importantly, the CMB has reshaped our understanding of cosmology itself. It's provided the first direct evidence for the Big Bang, confirmed the existence of dark energy, and offered clues about the nature of dark matter. It's challenged us to rethink our assumptions and explore new ideas, from cosmic inflation to the possibility of a multiverse. The CMB isn't just a tool for answering questions, it's a catalyst for asking them, pushing us to explore the universe's deepest mysteries. What's truly remarkable is how much we've learned from this ancient light. It's not just a relic of the Big Bang, it's a living record of the universe's history, a guide to its structure, and a window into its future. By studying the CMB, we've not only uncovered the story of where we came from, we've also gained insights into where we're headed, from the universe's ultimate fate to the forces that will shape its destiny. As we wrap up this journey through the CMB, it's worth reflecting on how far we've come. From its accidental discovery in the 1960s to the exquisitely detailed maps produced by missions like COBE, WMAP, and Planck, the CMB has transformed our understanding of the cosmos. But the story isn't over. It's just beginning. New missions and technologies promise to take our exploration of the CMB to even greater heights, offering insights into everything from the nature of dark energy to the possibility of primordial gravitational waves. So, what's next? If this journey through the CMB has sparked your curiosity, there's so much more to explore. From the latest research to the cutting-edge experiments that are pushing the boundaries of what we know, the CMB continues to be one of the most exciting frontiers in science. Whether you're a seasoned enthusiast or just starting to explore the wonders of the cosmos, the CMB invites you to dive deeper, to ask questions, and to marvel at the incredible story of the universe. The cosmic microwave background isn't just a scientific discovery, it's a testament to humanity's enduring curiosity and our drive to understand the universe. It reminds us that even the faintest whispers can carry the loudest truths, and that the journey to uncover them is as rewarding as the answers themselves. So, as you look up at the night sky, remember this: the universe's story is still being written, and the CMB is one of its most fascinating chapters. Let's keep exploring, keep questioning, and keep marveling at the wonders of the cosmos. The cosmic microwave background has captivated scientists and curious minds alike for decades, but you don't need a PhD to dive deeper into its mysteries. If this ancient light has sparked your curiosity, there are countless ways to explore it further, whether through books, documentaries, or even direct engagement with the scientific community. Let's take a look at some practical ways you can continue your journey into the fascinating world of the CMB. For those who love to read, there are several excellent books that bring the story of the CMB to life. The First 3 Minutes by Steven Weinberg is a classic, offering a vivid account of the universe's earliest moments and the discoveries that followed. If you're looking for something more recent, The Edge of the Sky by Roberto Trotta provides a beautifully written, accessible introduction to cosmology, including the role of the CMB. For a deeper dive into the science behind the Big Bang and cosmic inflation, Cosmic Jackpot by Paul Davies is another great choice. These books not only explain the science but also capture the wonder and excitement of exploring the cosmos. If you're more of a visual learner, documentaries and online videos can be a fantastic way to explore the CMB. PBS Nova series has several episodes dedicated to cosmology, including the CMB and the Big Bang. YouTube channels like PBS Spacetime and Kurzgesagt offer engaging, easy-to-follow explanations of complex topics, from dark energy to the origins of the universe. Many of these resources are free and accessible, making them a great starting point for anyone curious about the CMB. For those who want to stay up to date with the latest research, following scientific institutions and researchers on social media can be incredibly rewarding. Organizations like NASA, the European Space Agency, and the Simons Observatory regularly share updates on their CMB studies, along with stunning images and insights. Platforms like Twitter and YouTube are also great places to find lectures and interviews with leading cosmologists, offering a chance to hear directly from the experts. If you're eager to engage more actively, consider attending public lectures or events hosted by universities and science centers. Many institutions offer free or low-cost talks on topics like cosmology and astrophysics, often featuring researchers at the forefront of CMB science. These events not only provide a deeper understanding of the science, but also offer a chance to ask questions and connect with others who share your curiosity. For the truly adventurous, citizen science projects can be a way to contribute to real scientific research. Initiatives like Zooniverse allow anyone to participate in analyzing data from astronomical surveys, including those related to the CMB. While it might not involve peering through a telescope, these projects give you a hands-on role in the scientific process, making you part of the ongoing exploration of the cosmos. What makes the CMB so enduringly captivating is its ability to connect us to the universe's origins while also pointing the way to its future. It's a reminder that science isn't just about finding answers, it's about the journey of discovery, the questions that push us to explore further, and the shared sense of wonder that unites us all. Whether you're reading a book, watching a documentary, or attending a lecture, the CMB invites you to be part of that journey, to marvel at the universe's mysteries and to keep asking the big questions. So, as you continue to explore the cosmic microwave background, remember this: the story of the cosmos isn't just for scientists, it's for anyone who's ever looked up at the night sky and wondered how it all began. The CMB is your window into that story, a chance to connect with the universe on a deeper level. And who knows, maybe the next big discovery will start with a spark of curiosity from someone just like you. The cosmic microwave background is more than just a scientific discovery, it's a story that resonates with something deeply human. Its enduring allure lies not only in the secrets it reveals, but in the way it connects us to the universe's grand narrative. For scientists, the CMB is a treasure trove of data, a cosmic Rosetta Stone that deciphers the universe's origins, structure, and fate. For the public, it's a source of wonder, a faint whisper from the dawn of time that reminds us of our place in the cosmos. Together, these perspectives make the CMB one of the most captivating phenomena in modern science. What makes the CMB so compelling is its dual role as both a relic of the past and a guide to the future. It's a snapshot frozen in time, capturing the universe as it was just 380,000 years after the Big Bang. Yet, it's also a living record, offering clues about the forces that continue to shape the cosmos today. From the seeds of galaxies to the mysteries of dark energy, the CMB bridges the gap between the universe's fiery birth and its ultimate destiny. It's a reminder that the story of the cosmos is still unfolding, and that we're part of it, not just as observers, but as participants in the ongoing quest for understanding. But the CMB's appeal goes beyond science. It touches something universal, a sense of awe, curiosity, and connection. When we look at the CMB, we're seeing the universe's first light, the moment it became transparent and allowed photons to travel freely. It's a moment frozen in time, yet one that continues to shape our understanding of reality. This ancient glow reminds us that we're part of a much larger story, one that began billions of years before us and will continue long after. For scientists, the CMB is a puzzle that never stops giving. Its subtle temperature fluctuations and polarization patterns offer endless opportunities for discovery, from testing theories about inflation to probing the nature of dark matter. Each new mission, each new map, brings us closer to answering some of the biggest questions in science. And yet, for every answer the CMB provides, it raises new questions, inviting us to keep exploring, keep questioning, and keep pushing the boundaries of what we know. For the public, the CMB is a reminder of the universe's vastness and mystery. It's a symbol of our capacity for discovery, a testament to the power of human curiosity and ingenuity. The fact that we can detect and study this ancient light, billions of years after it was first emitted, is nothing short of extraordinary. It's a story of perseverance, of collaboration, and of the enduring human spirit that drives us to explore the unknown. As we prepare to wrap up this journey through the cosmic microwave background, it's worth reflecting on what it means to us, not just as a scientific tool, but as a source of inspiration. The CMB reminds us that the universe is full of mysteries waiting to be uncovered, and that the pursuit of knowledge is one of the most profound and rewarding endeavors we can undertake. It invites us to look up at the night sky with a sense of wonder, to marvel at the beauty and complexity of the cosmos, and to remember that we're part of something much larger than ourselves. So, as we conclude this exploration of the CMB, let's take a moment to appreciate the incredible journey we've been on. From the universe's fiery birth to the faint whispers of light that still linger today, the CMB has shown us the beauty, the mystery, and the endless possibilities of the cosmos. And as we continue to explore its secrets, we're not just uncovering the universe's story, we're